So, hello guys, welcome to another Problem of the Day series video where we are going to solve LeetCode and GFG problem of the day 27th. So, let's first solve the LeetCode problem of the day. So, the problem is subarray product less than k, and the problem statement given to us is given an array of integer nums and an integer k, we have to return number of contiguous subarray where the product of all the element in the subarray is strictly less than k. So we will be given some numbers in an array and we have to find all the subarray whose product is less than k. Not less than equal to k, just less than k. So as you can see, the first example, the nums are. So the constraint given to us are the one is between three nums, the length of the nums is between 1 to 3 into 10 raised to 4, and our nums of I will be between 1 to 1000. Okay, so given to us, the first example is the nums array elements are 10, 5, 2, and 6 in our k is 100. Now there are it's a total sub as you can say 10, 5, 2, 6, they are lesser sub, then 10 to 5, which is 50, then this 10, 6, 6, 5, 30, 30 into 260. So 60 is also less than 100, so this is included. Now this is not included because 50 into 200. So 100 is not lesser than 100. It is equal to 100. Hence it is not included. So one of our brute force approach will be to start iterating from zeroth index. Then we have an inner for loop which will start iterating from j equal to I, and it will move until n, and will find all the subarrays whose product is less than k. Then our I pointer will move to +1, and inside that j equal to I will move to I equal to n. So this will find our answer, but it is a brute force approach because the time complexity of this approach is big of n square, which will not fit in our constraints. So what would be a better approach? In our brute force approach, what we were doing is we are calculating the product of every subarray. Now, in this case, what we know is, first, let's take this example, okay? So, in this 10 and 5, this, okay, let's see this 10. Our 10 is already, which we know that 10 is less than 100, so it is calculated. Then we are taking 10 and 5 again. So, we know that our 10 is also included in our, 10 is included in our answer. And and 10 and 5 making iterating the sub array again will not make any difference to the product, uh, because we can find our answer by just by division of that number. So what we will do, we will in this approach we will use sliding window approach, where for every height and j pointer we will move towards the sub array which is still less than 100. So we will iterate till the number which are till less than 100. Okay. So as you can see, 10. So 10 is less than 100, then 5. 5 is less, 50 is less than 100, then 100. Now in this case you can see the 100 is not less than 100. So what we can do, here is a point that, uh, if we don't have any negative, or if we don't have any zeroth value, then going forward till a number which is lesser, which is greater than or equal to k, won't make any sense. Because it will always give product which is greater than 100. So as you can see, going forward after two, no won't make any sense. So what we can do is, if we found at certain point that this will make this number, if we found a certain point that subarray is making our number greater than k, or making our product greater than k, then what we can do is we can do a division operation on our product of the subarray from our zeroth index, or from our previous index. So this will help us to find. So this will make our product less than 100, or less than our given key. So let's go to let's go to the example step by step. So as you can see in the first step, it is I equal to 0 and j equal to 0. Okay. Now our product is 10 and our result is 1. as our as the product is less than k, our 10 is lesser than k, so and our result is updated to 1. Now in the step 2, our I will be incremented to 1. Now as our I is incremented to 1, if the product will be 50. Now 50 is lesser than k, hence our result will be 3. Now, you can see that our result is updated to 3 because we have two elements. Because for the result of 1, it was 10. For result 3, it was 5, and it was 5 and 10 of the subarray. So we can find this using our I and j. So the formula to calculate our current result will be I minus j plus 1. So why we are using this formula? Because our current subarray, uh, whichever number of whatever number of elements we have in our current subarray. So subtracting from the current pointer to previous pointer, suppose we have in a subarray we have a number. So suppose in our subarray we have number 1, 2, 3, 4, 5, and 6. Our I is pointed to 6 and our j is pointed to 1. Now in this subarray there are total 6 numbers. So our I will be 5 minus 0. So as you can see that 5 minus 0 is 5, which is plus 1, which is 6, which will give us 6. So as you can see that total number of sub-array from I till 0, this formula or the total number of all the numbers in that sub-array will give us our answer. Because if 1, then 2, then 3, 4, 5, 6. So let's take these three numbers. So our j is at 0, 1, and 2. Our j is at 2, and our I is at 5. So what is 5 minus 2? Is 5 minus 2 is 3. Our 5 minus 2. Sorry, our j is 3 and our I is 0. I is 5. So 5 minus 3 is 2. 2 plus 1 is 3. So this subarray, so we can find the total number in that subarray or in that window. So, and hence this will give our total subarray, which is 1, then 2, and then 3. So that's why we are using this formula. So in the third step, our j is 0 and our j is 0 and our I is 2. Now, as you can see, our product becomes 100, which is greater than or equal to 100. So what we will do in this case is we will use a while loop while our j is not equal to I and our product is greater than equal to k. So in this case, what we will do is as our j is at zeroth index. So we have to eliminate those numbers who are making greater uh, greater product than k. So as we want to eliminate this number, hence we can use a division operation. So this division operation will give us, so as you can see our product division equal to nums of j. So our nums of j currently is 0 and our product is 100. So our at 0 nums of j is 10. Hence if 10 divided by 100 divided by 10 will give us 10 and we will increment our j. So this operation is a post increment and hence it will do j after taking that value. And hence our result will be 5 as our so as you can see, our result will is 5 because 2 minus 1 plus I minus j plus 1 is 2 minus 1 is 1 plus 1 2. Hence we are getting the total number subarray. As you can see, the in this step 3 of total number subarray, we are getting a 2 and 2 and 5. Now in the step 4, our j is 1 and our I is 3. And in this case, our product will be 60 and our result will get updated to 8 because 3 minus 1 is 2 plus 1 is 3. 5 and plus 3 is 8. And that's how we can find our answer. So let's go to the code of this problem. So as you can see, we have a previous pointer set to 0, result set to 0, and a product set to 1. Now in the current pointer, we go from I from 0 to n. Then we have a product which is getting getting multiplied with current nums of element, which which current pointer is referring to. Now at now we have a while loop until our product becomes greater than until our product is greater than or equal to k. So we will use a division operation to remove the elements at the start which are making it greater, and hence at the end we will do a result plus equal current pointer minus previous pointer. So first one to find our result, or to find all the subarray in that window which are uh, contributing to the answer, and then we will return our result. So this will be it for this problem. The time complexity of this problem is big of n, and our space complexity is also big of uh, space complexity is big of 1, as we are not using any constant, as we are not using any space to store anything. So let's move forward to our GFG problem of the day. So the problem was find shortest safe route in a matrix. It's really a good problem for one of those who don't know much of BFS and DFS and recursion. So so problem statement is we are given a matrix with R rows and C columns. Now where some cells are landmines, so the landmines are marked as 0, and others are safe to traverse. Now what our task is to find the shortest safe route from any cell in the leftmost column to any cell in the rightmost column of the mat. So we have to find the shortest route from this column till the last column, from I equal to 0 to I equal to 1, 2, 3, 2, till I equal to 4. Now, the conditions are given to us are you cannot move diagonally. So, we cannot move diagonally, and you must avoid both the landmine and the adjacent cell, up, left, down, right. So, given a landmine to us, we cannot also go to its adjacent cells. Like its zero adjacent cells are this one, then this one, and this one. So, we cannot move to these cells. Now, as they are also unsafe. So these are all the given conditions. So this is our input example one, and this is our result, which is 6. So as you can see, our safest route is from j equal to 3. So this will be the safest route. Why we are not going here, it because it is adjacent to a landmine. Why we didn't go here, because this cell is adjacent to a landmine, as we cannot go over there. Okay. It's given as -1 because whichever path we try, there is a landmine which is making its adjacent unsafe to travel. This one, and this one. Hence, the output given to us is -1. So our constraints are R and C is between 10 raised to 3, and the values present in our mat will be 0 and 1. Okay. So let's go to the explanation of this problem. So this is our given matrix. So in the first thing what we will do is, so the first thing whatever hindrance is, we don't know, or uh, it will be difficult to find what which elements are landmine, or which uh, path is not safe to travel. So in this case, what we will do is we will make a array, we will make a matrix where all the landmines which have its adjacent, so we will have traverse a landmine, and we will make it all is adjacent to one. In the first step, we will do this. Now you can also handle it during your code, but you have to make an extra function is safe, which applies all the condition and check if any of its adjacent cells do not have any landmines or 0 or not. Because so in this, in the first step I will make all the cells whose adjacent cells are 0. So you can see this is our given matrix, and I have converted it into I have converted all the cells which are unsafe to travel. So as you can see, the 0 is here. So I have made all the cells of left, right, and down as 0. It is given as 0. So all these adjacent cells I have made as 0. So let's take this example. Okay, let's take this example where we start from I equal to 4. Okay. So as you can see that we have to move towards the adjacent cell, or we have to make a recursive call toward each adjacent cell. So in this step, as we are at certain position, what we will do, we will make a adjacent, we will traverse towards adjacent cell using recursive call where of I plus one, I minus one, j plus one, and j minus one. And we will have a condition, we will have a base case where we check if any of our uh, pointers or any of our variables are not exceeding the mat boundaries. So you can see that this is going to is up, down, and it towards its right side. So let's take an example where it first go toward its right side. You can see this is our matrix where we have reached here. Now it will go towards its up, right, and down. So let's first take its downside. Now you can see that cross indicate the cells are already visited. So our current index ing is here. So it will try to move its upper side, but its upper side is already visited. Like we will have something which indicates that that field is already visited. So we will take care of that, and then it will go towards back. It can go towards its back side, but it won't make sense to go towards its back to go towards its back because it is already coming from that row. So we can go toward its back and check if that uh, cell is visited or we have to traverse the cell. But it will be fine if we don't go toward back. We will still get our answer. So it will go toward its right side. And in the next step, you can see this both are visited, and this one we are getting here is our current cell. Now, you can see the current cell don't have any place to visit, or is adjacent are unsafe to travel, or some of the adjacent are already visited. So in this case, what we will do, we will return a max value, uh, infinite value, which will indicate that this is not the part that we can take. So to move forward, return a max value, and then you can see that this has now this have don't have any way to travel, so it will move back and return a max value. So now as you can see let's go toward the right side. As you can see the right side is already zero and it is not unsafe to travel, then we will return a max value to indicate that this is not a safe way to travel. Now let's go above. So you can see this is visited. Now it will go towards its up and right on its right side. Now its above is unsafe to travel, so it will return a max value. Now as you can see that this one and this one is already visited, and now we are current cell. Now this current cell can't move toward its down and can't move toward its right because they are both unsafe. So it will move up. So in this step, ing is here and it will move toward his right side because there is no way he can travel to his adjacent except the right side. Now this is where our current ing pointers are, and you can see it can move to two of its adjacent cell. One is at right and one is above. So the above one go will go to the above, and now as you can see, these all cells are visited. It will go above and check which cells it can travel. So it can only move toward its right cell. Now we have found out a path, or we have found a condition where we have reached our last column. So to check if we reach our last column, we will have a case where our j is equal to m minus 1. Indicate our j is equal to m minus 1, indicate that we have reached our last column. So as we have reached our last column, we will return a 1, indicating that this cell is the last cell of the column. So we will return a 1 to it. Now and this will return a max value to it. This will return a 1 to it. So between the max and 1, we will find out which will be our minimum value, and we'll return plus 1 to that because this cell we have visited, and therefore we are adding a 1 to it. Hence we will return 2 to this because you call. So you can see we are at this position. So at this position now we don't have any way to go to any of the adjacent cells are remaining. So in this case, okay. So in this case, if we return to its right position, and in this right will be our last element, so it will return a one because this is the last element indicating that it is a last column. So it will return a one to it. Now from two and one, we will find out the minimum and we return plus one to it. So in the both of them, the minimum is one, and we return plus one, which will become two. Okay, so in this case, now it cannot go any of the adjacent cells. From it here, it will return a max value. From here, it will return a max value, and from here, it will return a two value. So from all three of them, the minimum is two, and two plus one three, so it will return a three from here. Now, as you can see, there are no way to travel any of its adjacent cells, so it will return a three as three is the minimum value. So three plus one, it will return four towards this cell. Now, there are no cells that it can traverse, so it will return from this it will get a 0, and from this it will get a 4. So it will go 4 plus 1, which is 5, and it will return 5 to it. Now we have traversed towards its right, we have traveled toward its down and up. So for, this is giving us max, this one is giving us max value, and this one is giving us 5 value. So minimum of them is 5, so hence we return 5 plus 1, which is 6. So here it is returning 6. Now, as you can see, it will move above its. So now we have traveled toward its right direction. Now we will move toward its up direction. So as you can see, that up direction, this cell is already visited. Now this cell is already visited in our this recursive call. You can see where is it? Oh, sorry. So this cell, it will move toward this cell. Now it will move towards this cell and this right side cell. So it's you can see that this right cell is already visited in our previous calls, one of his calls. So this is the cell which is already visited. Hence, we will this indicates that we have to store our result in some uh, array so that we don't have to recompute it. We don't have to compute this the value again. So in this case, as it will see in, in our DP array that this position value is already calculated, as it will return the stored value, indicating that this will be our answer. So as you can see, at till this position we got four. So is it one, two, one? Okay, sorry. So till this position we got four. So it will return four plus one, which is five. Total number. So let's check the total number if the total is correct or not. One, two, three, four, five. So it will return a five to it. Yes, and above this will return a max value to us. So the so in this cell we give of us a 5 to us. So for in this cell we are getting a 6 and in this cell we are getting a 5. So we return a minimum value plus 1 which is 5 plus 1 to our main recursive call which is 5 plus 1 which is 6. So hence our 6 will be our answer of this example. So let's go to the code part. So in the first step I am finding all the zeros which all the position where 0 is in our mat, and I'm storing in a 0 position array list. Um, and then what I am doing is I'm iterating over these 0 positions at a list, and getting all the I and j uh, position where the zeros are present, and move and doing all of it, and for all of it adjacent I am making them 0. So I plus 1, so down it will make it 0, and above it will make it 0, and so, similarly it's left and right position. So this will make sure that all the unsafe cells are considered at first. Now, now for this column, I am iterating all of its cells because I am iterating all of its cells because there might be certain condition that in one of these cells we are having a zero. So as in the so if I make just one call, if it is a certain position I got a zero, it will just return the value. It won't go toward any of its down values. Hence I am iterating over this column. So as you can see, I am making a shortest path function, which will call to mat I is the current ith index or the current row, and the j is zero, as we have to start from zero column, and n is the n is the length of our mat. Now this is a base condition which will check if our I and j are not exceeding our boundaries and our mat, and it will check if our mat have a zero at zero or it is unsafe to traverse this cell. Now in the second condition we have j equal to m minus 1, indicating that we have achieved our one of our goals. So as so it will be considered that we have reached our last column, and then we will return a 1. And you can, as you can see, in this case we are returning a max value. Now this will make a call towards adjacent cell, 1 to the down, I plus 1, 1 towards is up, which is I minus 1, and 1 towards is right, which is I comma j plus 1. Now at first what we will do is we will make our mat of I0 as ij is 0. Why are we are doing this? Because as we have, as now this cell is 1, and we pass all our base cases. Okay, so in this case we will make it 0 because we don't want it to be visited again. We don't want it to be visited again for pre-competition, as we have to we have to make sure somehow, or by taking some visitor array, extra array, or by modifying this array, we have to make sure that we are not revisiting that cell from whichever cell we are coming from. Hence, I am updating its value to 0. Then we have a result which is taking integer or max value. Now, after all this call, we will make our mat of ij as 1 as its older value, because our goal is completed. So we are updating toward is what was it last value. Now in this we are checking if any of our uh, now in this case we are checking if any of our adjacent cell gives us maximum value or not. Now why we are doing this? Because if I add a plus one to its integer or max value, it will go towards its limit because it is an integer, and it's integer it is a max value of any integer. If I do a plus one, it will go toward it will give me a minus integer. It will give me integer minimum value, which in this case will be wrong as I am using main. Hence, I have to first make sure that the answer that I am getting is integer max value or not. Similarly, I am checking for up, and similarly I am checking for down. Now, as I am getting a mid result at that certain position, I am storing it a DP array. And as you can see, this is a condition where I am checking if that DP DP array has certain value at this I and j position or not. And if that position, if there is a position, then it will just return that value. And then after iterating all this column, we will have our result with the minimum number of shortest part. Now, as you can see that I am checking if our result is integer or max value or not. If it is, we are returning a minus one, and if not, we are returning a result. So in this case, so that's how we can achieve our solution. So that as you can see, time complexity of this approach is big of n square, and the space complexity is also big of n square. So because we are iterating over the mat, so this takes big of n into m. Then this won't take. So if all the values are 0, so in this case, the worst case it might go to big of n into m. Then this will go till big of n into m. As you can see that we are just iterating over all of its value. We are just treating all of its adjacent cells just once and making sure that we don't revisit a certain index from whichever we are coming from. So this will take big of n into m. So the time complexity big of n into m, space complexity is also big of n into m, as we are having an extra DP array of n into m. So you can avoid using this. So in this case, what you can do, we can avoid using this extra for loop by creating a if function where you just check if this I plus one lesser than n and its value is not zero. You can check for all this condition, and that's how you can avoid this. I am doing this in a video too, so that we can get a easy view of what we want to do. So okay, that's how you can avoid this for loops. So guys, this will be it for the day. I hope you got my explanation, and I hope you enjoyed my video and got a view of how to move forward or how to approach this kind of problem. So this will be it for the day. Uh, Thank you.